All right, we're gonna go over the bubble tube lab. So you should by now have your data graphed on graphical analysis, and you should have all of the questions in the lab answered. If you have not done that, you need to go back and answer the questions first before you watch this video going over it, because if you don't have a chance to think through these things on your own first, you're not gonna get nearly as much out of it. So first we're gonna start with the pre-lab, even though we may have gone over this together in class. The first question says, write a sentence that relates speed, distance, and time. This is a question that you also had in those intro motion questions. And we had some good examples of one. Here's mine. The faster you go, so the more speed you have, the more distance you cover in less time. You could write a couple different versions of this. You could say, however much distance you cover in so much time tells you your speed. You can have a couple different versions of this. Then, when we looked at, before you started the lab, we looked at all three tubes. And you should have noticed that the red one was the fastest. The red one, the bubble went from one end to the other the fastest. So now, you're graphing distance versus time of the bubble in each tube. So will the fastest bubble move more or less distance in each second compared to the slowest? The fastest bubble means that it's going to cover more distance per each second compared to the slowest one. Number 4, predict which bubble tube will be most similar to which graph. Think about how steep the line is and how speed relates to how much distance the bubble travels in a certain amount of time. So if we look at these three graphs right here, y-axis is distance, y-axis is distance, x-axis is time. So if it's covering more distance in the same amount of time, then it's going to be going the fastest. So this one would match up with the red. It's covering the most amount of distance. If we look at the time from here to here, it's covering more distance in that time compared to the same amount of time. Blue is covering less distance in that amount of time, and green is covering even less distance in that amount of time. You should have your data on here and then a graph on paper as well as the graph on graphical analysis. This paper graph I want you to do because it is a good practice of practically what does this graph look like? What does it look like if you cover 15.1 centimeters in 1.09 seconds? The graphical analysis graph is useful because it does actually give you the equation and the slope for the line. It does those calculations for you. Question number 1, how far did the bubble in the green tube travel in 6.5 seconds? So if we are looking for the green tube, how far did it travel in 6.5 seconds? So we could look from, for example, we could look from 5 seconds to 11.5 and see how much distance they cover in that time, and it's about 25 seconds. Your answer here should be close because all of the green tubes are the same, all of the blue tubes are the same, all of the red tubes are the same. How far did the bubble in the red tube travel, and how far did the blue tube travel? So again, we can look at our data, our lines, and say, okay, in 6.5 seconds, so maybe since these lines are steeper, maybe we want to start down here. So maybe we want to start from about 1 second to 7.5, and how much did each of them cover in that amount of time? So that it would be 55 and 45. The red one is the fastest, and the red one did have the steepest line. So what's the connection between these two questions? Well, if it's the fastest, it's covering the most amount of distance in the same amount of time, which means its change in slope, its change in distance, its change in the y-axis is the greatest per the amount of time. You can look on your graph, or on the graphical analysis graph to find the M, and that graphical analysis graph should have already calculated that for you, so all you're doing is copying down these numbers. But again, your data should be similar to mine because all the red tubes, all the green tubes, all the blue tubes are each the same relative to their color. All right, if slope is rise over run, so change in y over change in x, what are the units for the slope on this particular graph? So if our y is distance and our x is time, that means that our slope is change in distance over change in time, and our distance is in centimeters, and our time is in seconds. So the units for slope are going to be centimeters per second. And what's the equation for speed? Speed is distance over time. That means that if slope is distance over time, or slope is change in distance over change in time, and speed is distance over time, then our slope tells us our speed. So then how does the steepness of the line relate to the speed? Well, the steepness is related to the slope. If we're going to have a steeper line, we're going to have a greater slope, so we're going to have a greater change in distance over time, so we're going to have a greater speed. All right, so let's look at what these lines mean on here. This is similar to what your graphical analysis graph should look like. We've got the axes labeled, we have the 3 lines, and then we also have the equations on there. So looking at these 3 lines, if we look at one at a time, let's look at just the green one. At any point on that line, does the slope change? So if we look at point right here, what's the slope? Compared to if we look at a point right here, what's the slope? If this is a straight line, the slope is the same at any point. So if that line is straight, that means the slope isn't changing. So if the slope isn't changing, does the speed change? Remember that the speed is equal to, or the slope tells us the speed. So if the line on a distance versus time graph is straight, that means the speed is not changing. It means the speed is constant. The speed is whatever it is, it's constant right here, it's the same right here, it's the same right here, it's the same right here. The slope is constant, so the speed is constant. A straight line, again, on a distance versus time graph means constant speed. We are going to be doing more with motion graphs like this, looking at distance versus time graphs, and what does it mean based on what the line looks like. Now, what if the line were curved? What if the line looked like this? What does that mean about the speed? So, if the slope is not constant, if the slope is not a straight line, the line is not a straight line, that means the speed is not constant because the slope at any given point is going to be different. What's the slope right here? Is that different than the slope up here? And if the slope is changing, the speed is changing. So let's look at each one of these individual points. First one down here, the slope at that individual point is about that, a relatively shallow line. So that means your speed, if your slope is not great, your slope is shallow, that means your speed is relatively less. Whatever's going on right here, it's not very fast. But if we look at the next point, the slope at the next point on the graph is a little bit steeper. That means the speed is going to be a little bit greater. If we look at the next point, the slope is a little bit steeper, which means the slope is greater, the speed is greater. If we look at the next line, the slope is greater, which means the speed is greater. So if the slope continues to increase, when we have a line that's curved upward like that, the slope is increasing, the speed is increasing. So if our slope changes, that means our speed changes. And if our speed is changing, that's what we call acceleration. The definition of acceleration is a change in speed or velocity.